When you increase the magnetic flux here, okay, you increase the electromotive force, it will increase the current. The current will increase the magnetic field. The magnetic field will increase the magnetic flux. When the magnetic flux increase, you will get the you will get the induced EMF. The EMF here is for the electromotive force. So I may write this as a EIND, the electromotive force. This is the induced electromotive force that comes from the increasing of the magnetic flux. Comes from the increasing of the magnetic flux. Okay. Now, what is the direction of this induced EMF? What is the direction of this induced EMF? Can you remember just Monday, 3 days ago, you use the Faraday's law. When the magnetic flux increase, you will get the induced EMF, and when you have the induced EMF, the direction of the induced EMF will, in this case, the direction of this induced EMF will try to reduce the magnetic flux. Okay? We'll try to reduce the magnetic flux. So, now the flux increase because the magnetic field increase, and the magnetic field increase because the current increase. So it means that the EMF will have the direction that try to reduce the current, right? So it means that it try to reduce the current, try to reduce the current. So it means that if we look the EMF as you add the new energy source to the system, it means that this induced EMF will act as a new energy source like this. Okay? This comes from the induced EMF. Why I say that is like you add the new energy source. You can see that the new energy source has a positive pole here, the negative pole here, and it will reduce the current. The current will pass from the positive to negative side of the energy source. Like if you look at this part, so it starts from this part, the positive to the negative. But if you place the new for example, battery into the circuit like this, it will try to create the induced current. I may call it induced current in the opposite direction to the original current here. So it means that it's equivalent. We can equivalently say that we put the new battery into the circuit to produce this induced current, and this induced current will try to reduce the total current in the circuit. Okay? So it means that the original energy source need to put more energy to to create the current in the circuit, right? Because it has to overcome the effect of this induced EMF. It has to overcome the result of this induced EMF. So it needs to put more energy to the system. And this additional EMF, we will define from this additional EMF, we will define a parameter that tell us that if you have a wire like this, a circuit like this, how much energy that you have to put to the system to sustain this current, okay, to sustain this current I from the original source. Okay, so we define a parameter, we call it L here. This parameter L. This parameter L. And we call it the inductance. The inductance of the circuit or of the while loop. And we define this inductance is equal when we multiply this inductance to the rate of change of the current. Okay, you can see that di by dt is the rate of change. Is the rate of change of the current. Okay, and we say that when we multiply this inductance of the loop with the rate of change of the current, it will equal to the induced EMF. Okay, now we change the symbol a little bit. We change it to the EL to tell us that this is the EMF that comes from the induction. Anyway, this term is the induced EMF that comes from the change of the magnetic field in the loop. You can see that this is interesting that we define the induced EMF from the inductance and the rate of change of the current. What will happen if the di by dt equal to 0? What will happen if di by dt is equal to 0? If di by dt equal to 0, it means that EL is 0, right? And when we look back to this circuit again, it means that we don't have this additional energy source if the current is not changed in time. That is reasonable because if you look back to the Faraday's law, we have that the EMF is equal to the minus of d phi by dt. This is the Faraday's law, right? It means that you will have the induced EMF only if the flux change in time, right? You will have the induced EMF only when the flux change in time. And how can we change the flux here? This is the flux. Okay, I can write the magnetic flux. How can we change the flux here? The flux can be changed when we change the current, right? When you change the current, the magnetic field change, and when the magnetic field change, the flux change, and when the flux change, it will induce the electromotive force in the circuit. So it means that if the current does not change, if the current does not change, the magnetic field does not change. And when the magnetic field does not change, it means that d phi by dt is 0. And d phi by dt is 0, it means that the EMF is also 0. So, we will have the induced EMF in the circuit only when the current